When using a metric algorithm, the first step one usually takes is normalizing the data. That is, scaling it, so for every feature its mean becomes equal to 0 and its standard deviation becomes equal to 1. But why do we scale all the features to the same size? Maybe the features differ in impact on target and should be weighed accordingly. There is a customizable metric, Mahalanobis distance. We will first explore its formula and then examine a way to fit it to a specific task. Mahalanobis distance between 2 points u and v is computed using the following expression, where matrix A is a parameter. Let's insert specific matrices A and see what will happen to the metric. If A equals identity, we have square root of u minus v transposed multiplied by u minus v, which can be seen as scalar product of vector u minus v with itself. That's Euclidean distance. So Mahalanobis distance with identity matrix A is equivalent to Euclidean distance. Let's experiment more. Now we will denote A as inverse matrix of features variances. This means A will have inverse variances of individual features on its diagonal and zeros elsewhere. At this time Mahalanobis distance computes Euclidean distance with coefficients of differences in features proportional to their variances. This is the same as normalizing the data and then calculating Euclidean distance. In fact, SciPy spatial distance module has as Euclidean function for this specific calculation. Let's also note that Mahalanobis distance with extremely small weight to one feature is equivalent to dimensionality reduction. Indeed, with weight this small, any change in corresponding feature will hardly impact computed distance. But how exactly will Mahalanobis pick up on patterns in our data? We are going to configure it using least margin nearest neighbor, or LMNN for short. For each object, which we will call anchor, we will construct a set of objects, which should be as close as possible to anchor, as well as a set of objects which should be as far as possible from anchor. The set of close points will consist of anchor's k closest neighbors from the same class. The set of distant objects will consist of all the points from other classes than anchors. With the sets defined, we will minimize the following function, called triplet loss. It is named triplet loss because it is a sum over triplets of anchor object, anchor's close object, and anchor's distant object. First term of triplet loss penalizes for difference in embeddings of anchor object and its close object. Second term of triplet loss penalizes for distance to distant object being less than distance to close object plus 1. You might wonder why there is a constant. If there was no 1, the whole triplet loss could have been easily minimized by making all embeddings equal to 0. Constant's role is making this trivial solution impossible. Now let's apply least margin nearest neighbor to data with hopes that it will learn scales that can ease used algorithm's job. We will solve a classification problem using k nearest neighbors classifier as our base algorithm. The problem will have two features, and target will depend on only one of them. We run k nearest neighbors classifier on data with no preprocessing, with Euclidean distance, and with metric learned on it using LMNN, as well as on data scaled with standard scalar with Euclidean distance, and with metric learned using LMNN on the scaled data. Note that these two learned metrics may differ. On quality graphs we see that unscaled approaches score worse than scaled ones, with LMNN with standard scalar being almost equivalent to standard scalar only. By looking at learned Mahalanobis matrix for k equals 20, we also notice that the feature correlated with target gets bigger weight than the independent one, showing that LMNN learns to pay more attention to important information. Let us now solve a classification problem in 6 dimensions. We create targets such that first two features have different level of impact on it, while the last two features and target are completely independent. Repeating the same experiment, this time we see standard scalar plus LMNN performing significantly well, scoring a % above standard scalar only and LMNN on unscaled data. Printed Mahalanobis matrices show that third and fourth features are weight more, though LMNN didn't catch that the last two features are useless. The higher dimension of our problem and the larger our dataset is, the more impact least margin nearest neighbor will have. So if you desire to push quality of your metric algorithm a bit higher, consider metric learning.